In the vastness of the universe, there is a place so staggeringly empty, it defies everything we thought we understood about existence. A hole so enormous it could swallow thousands of galaxies whole and still crave more. This is not the quiet distance between stars or the gentle gaps between galaxies. This is a region where galaxies themselves are simply absent, a colossal void carved into the very structure of the cosmos. Astronomers call it the Bhuta's void. Its discovery didn't just surprise scientists, it shook the foundations of cosmology, raising haunting questions about why such emptiness exists at all. What force created this monstrous hollow? Why do only a handful of lonely galaxies drift inside it? And what terrifying truths could be hidden within this great nothingness? Today we're diving headfirst into the darkest, quietest place in the known universe, where silence reigns and reality feels broken. So if you're ready to uncover one of the strangest, most unsettling mysteries of the cosmos, join us on this journey. Like the video, subscribe for more awe-inspiring discoveries, and prepare yourself because we are about to enter the void. Across the infinite canvas of the universe, light stitches together a glowing tapestry. Billions of galaxies bound by invisible threads of gravity, each shimmering like a lantern in a boundless night. But then there is a rip in the fabric, a place where the light falters and the threads unravel, leaving behind an unsettling, colossal hollow. It is called the Bhuta's void, and it should not exist. Imagine standing at the edge of a vast ocean expecting crashing waves, distant islands, teeming life, only to be met by a motionless, endless expanse of black stillness. That is what astronomers felt when they first peered into this abyss. A hole in space, so vast it could swallow 1,000 Milky Way galaxies and still hunger for more. This isn't merely a blank stretch between stars or a common cosmic gap between galaxies. This is a region of near total absence, where matter itself seems to have retreated, where the gravitational scaffolding of the cosmos has vanished, leaving only emptiness in its wake. We live in a universe where structure reigns supreme. From the smallest atom to the grandest galactic supercluster, the universe builds intricate patterns. Matter clumps, organizes, networks itself into the stunning web of filaments we observe in the cosmos. In every direction, our telescopes find galaxies glowing like the cities of a vast interstellar world. They should be everywhere, scattered like distant campfires across an infinite desert. But then, this void appeared. A staggering expanse, 330 million light-years across. Light, travelling at the unrelenting speed of 670 million miles per hour, would need 330 million years just to cross it. In the language of cosmic structures, this is an anomaly of the highest order. No known model of how the universe formed could justify a region so devoid of galaxies, so lacking in the vibrant dance of cosmic birth and death. Cosmologists tried to find comfort in randomness. They whispered, perhaps this is just a statistical fluke, a product of chance. Yet their equations rebelled. Their simulations refused to replicate such a void, and the universe, always a patient instructor, seemed to stare back, daring them to explain the inexplicable. Mainstream cosmology holds that after the Big Bang, tiny fluctuations in matter density seeded the structures we see today. Like ripples frozen in the fabric of space-time, these fluctuations formed clumps of matter that eventually birthed galaxies, stars, and planets. Over billions of years, gravity pulled and shaped these clumps into filaments, sheets, and clusters, forming the grand cosmic web. And yet, in this one vast corner of existence, the process failed. Here, gravity's song is muted, and the symphony of galaxy formation silenced. As we drift into this cosmic emptiness, a haunting question emerges: is the Bhuta's void an error in the universe's design, or a hidden truth we have yet to understand? Some voices in the scientific wilderness have dared to question deeper truths. Fringe theories speculate on ancient collisions between universes, scars left behind by primordial bubbles during cosmic inflation, or even massive concentrations of dark energy banishing matter from these regions. Though unproven, such speculations serve as the echo of human curiosity when confronted with the unknowable. What lingers beyond the silence is this: the Bhuta's void is more than an empty hole. It is a cosmic contradiction, a reminder that nature's laws may have exceptions, vast, silent exceptions that stretch across hundreds of millions of light-years. And yet, even within this gaping chasm, secrets shimmer. There are survivors in this desert, beacons within the void, sparse, dim galaxies whose mere existence poses deeper mysteries. But before we meet them, we must return to the moment humanity first stumbled upon this abyss. A moment of discovery, of shock, of wonder, and the start of a journey into the loneliest place in the known universe. It began with a telescope pointed toward an unassuming patch of sky in a constellation named after a herdsman, Bootes. The year was 1977, a time when the instruments of astronomy were far less powerful, but the hunger for cosmic understanding was no less fierce. Robert Kirshner, an astronomer driven by wonder, was mapping the distribution of galaxies, expecting to find the usual, a glittering sprawl of distant lights, each one a galaxy brimming with stars. Instead, he found nothing. Nothingness is a strange companion for a scientist. It unsettles, it whispers doubt, and it provokes. Kirshner stared into a stretch of space so barren that even the faintest glow of distant galaxies failed to emerge. Not a glint of cosmic dust, not a trace of star clusters, just a black wound carved into the cosmos. It defied his expectations, his calculations, and all known maps of the universe. The discovery was at once exhilarating and terrifying, for in the dance of science, anomalies are rare guests. They either herald an error in measurement or the promise of revolutionary truth. Kirshner's void was no mistake. Survey after survey, telescope after telescope confirmed the haunting reality, an immense gulf, devoid of matter, cutting through the universe like a silent canyon. What made this emptiness more unsettling was the backdrop against which it stood. By the late 20th century, humanity's understanding of cosmic structure had grown sophisticated. The prevailing belief was of a homogeneous universe, where matter, though clumped into galaxies and clusters, was evenly spread on large scales. Space was stitched together by a cosmic web, where every thread hosted countless galaxies, and every gap, though vast, was punctuated by the glow of distant light. But here, the web had torn. The Bootes void didn't fit within the neat models. It was a region of darkness more profound than anything previously catalogued. Kirshner, initially skeptical of his own findings, pursued the truth with meticulous care. His research revealed an expanse 330 million light-years in diameter, a cavern in the cosmos, so large it mocked human comprehension. Imagine, for a moment, shrinking the Milky Way, our home galaxy, to the size of a single coin, a shining silver disk in the cosmic dark. You would need to throw 1,000 such coins into the void just to begin filling it. Even then, the chasm would yawn wide, swallowing everyone without hesitation. The void was not a mere absence. It was a gravitational enigma, a question mark burned into the tapestry of the universe. Other astronomers were drawn to the mystery like moths to a flame. Their findings confirmed Kirshner's nightmare. This wasn't a statistical fluctuation or a hidden veil of dust. The Bootes void was real, and it was colossal. Its discovery forced scientists to revisit the assumptions they had comfortably leaned upon. The universe was supposed to be predictable, its structures explained by the elegant mathematics of gravity and the cooling embers of the Big Bang. And yet, here was a scar that defied those explanations. Among the quiet halls of observatories and in the lively debates of academic journals, theories blossomed. Some cosmologists suggested that the void was a product of random chance, a low probability blip in the grand lottery of cosmic formation. But simulations scoffed at this idea. To generate such a vast emptiness by mere randomness required odds so astronomical that they strained credulity. More daring hypotheses emerged. Perhaps the void was born during the epoch of cosmic inflation, an ultra-fast expansion that had stretched the universe just moments after the Big Bang. Some proposed that regions of space might have undergone uneven inflation, leaving behind pockets of high and low density. Could the Bootes void be a fossilized remnant of those first flickers of existence? Others peered into the mysterious realm of dark energy, the enigmatic force accelerating the expansion of the universe. They whispered of localized concentrations of dark energy, regions where its repulsive strength surged, pushing matter away and carving voids into the cosmos. These ideas danced on the edge of mainstream science, tantalizing but unproven. Even more provocative were the fringe voices that spoke of collisions between universes or cosmic bruises left by ancient bubble universes that collided and scarred our own. These were not accepted by the cautious majority, but in the face of the Boots void, even the most reserved scientists could not entirely dismiss the extraordinary. Yet, beyond speculation, the observable reality stood firm. The Boots void was there, silent, unblinking, and patient. It became a beacon for astronomical studies, a cosmic paradox that challenged every model of structure formation. In the decades following Kirshner's discovery, technology advanced, telescopes grew larger, detectors more sensitive, and computational models more intricate. Still, the void remained an unsolved mystery. It became more than a cosmic curiosity. It was a symbol of the universe's vastness, of how little humanity truly understood about the cosmos in which it floated. For Kirshner himself, the discovery was a lifetime imprint. He would later call it the Great Nothing, a name that echoed the void's silent grandeur. His work sparked generations of research, from radio waves to X-ray surveys, each peeling back a layer of the universe's secrets, yet always returning to the gaping absence within Boots. In the end, the Boots void is more than just a hole in the universe. It is a mirror. It reflects the fragility of human understanding and the endless horizon of cosmic mystery. Every discovery, every answer, seems only to reveal deeper questions. In that empty stretch of space, we are reminded that the cosmos is not a solved puzzle, but a living, breathing enigma, one that will outlast civilizations, outshine stars, and stretch beyond the reach of comprehension. And so, with Kirshner's revelation as our lantern, we step further into the void, to explore its depths, its dimensions, and the strange, lonely survivors that flicker within its vast, empty heart. Step with me now, deeper into the silence. Imagine hovering in the emptiness far from any star, drifting in a realm so vast that time itself seems reluctant to cross it. Here in the Bootes void, our usual measures of distance, size, and even thought begin to collapse under the sheer weight of scale. To understand this abyss, we must abandon the comfortable familiarity of kilometers and miles, and turn to the language of light years, where the very speed of light, the fastest phenomenon known to us, becomes a slow traveller against the expanse. At 330 million light-years across, the Bootes void is not merely large, it is a violation of cosmic expectation to traverse from one end to the other. A beam of light must journey uninterrupted for 330 million years, a time span longer than the age of complex life on Earth, longer than the rise and fall of continents, longer than memory itself. Every second we speak, light rushes through the universe at nearly 300,000 kilometers per second, circling Earth 7 times in a single heartbeat, and still, in the Bootes void, light barely makes progress. Scientists have tried, through metaphor and analogy, to bring this scale down to something the human mind can grasp. Shrink the Milky Way, with its 200 billion stars, its swirling spiral arms, its colossal central black hole, to the size of a single silver coin. Now imagine tossing this coin into a vast black arena. To match the size of the Bootes void, you would need to throw 1,000 such coins, scattered thinly across a darkness so immense that their light would never meet. Yet even this mental image fails, for the emptiness stretches far beyond our capacity to visualize. In more earthly terms, this void dwarfs our world in ways almost comical. The distance from Earth to our moon, which once seemed an impossible journey, is barely a whisper compared to the void. The span from our sun to the furthest edges of our solar system is an invisible grain of dust, lost within its expanse. The entire Milky Way, from edge to edge, would be an insignificant island swallowed whole. Even the local group, our galactic neighborhood including Andromeda and dozens of smaller galaxies, would drift unnoticed within this cosmic hollow. Yet, the Bootes void is not an empty bubble floating in isolation. It is carved into the very structure of the universe. The cosmos we observe forms an intricate latticework known as the cosmic web, a grand network of filaments, clusters and sheets, connecting galaxies across billions of light years. Like a living organism, the universe distributes its matter along these filaments, where gravity's pull has sculpted regions of high density, cradling galaxies in their gravitational embrace. Between these luminous threads, voids naturally form, vast underdense areas where galaxies are sparse but still present, interspersed like forgotten lanterns on a lonely road. These voids are common in cosmic structure, typical and expected, yet none compare to the vast chasm of Bootes. In most voids, you might find hundreds, even thousands of galaxies lazily scattered across the darkness, their light weak but unmistakable. In Bootes, the count plummets to single digits. Astronomers calculated that, given its size, the Bootes void should host at least 2,000 bright galaxies, yet surveys reveal only eight lonely galaxies adrift in an ocean that should be vibrant with cosmic life. This underdensity, this statistical emptiness makes the void a glaring anomaly, a wound in the expected smoothness of the universe. To chart this absence, astronomers deploy powerful tools. Radio surveys map the faint whispers of hydrogen gas. Optical telescopes trace the delicate glow of distant starlight. X-ray and infrared observatories search for hidden structures, for the invisible mass lurking behind the darkness. The void is dissected, measured, scanned, its contours precisely defined. Its diameter fluctuates slightly depending on the method of measurement, but the consensus remains 330 million light-years of near-nothingness. Yet even with our modern tools, the void refuses to surrender its secrets easily. Its boundaries are not smooth but jagged, riddled with cosmic peculiarities. In some areas, galaxies crowd together just outside the edge, forming dense wall structures known as void walls. These walls are the universe's last stand against the consuming emptiness within. A stark transition where the lush density of cosmic civilization abruptly ends and the void begins. Some scientists liken these walls to the ridges of ancient craters on Earth, the remnants of violent events that carved out a central emptiness and left behind a towering perimeter. Could the Bootes void be a relic of some ancient cosmic violence, a collision, a repulsive gravitational event, or a remnant of early cosmic phase transitions? Mainstream science holds cautious skepticism. The dominant belief remains rooted in the principle of large-scale uniformity, that over sufficiently vast distances, matter should distribute relatively evenly, voids included, and yet, the Bootes void stands as a defiant outlier, a statistical sore thumb protruding from the elegant models of cosmological evolution. An odd and less discussed curiosity arises when considering the psychological effect of studying such a structure. Astronomers who peer too long into this vast absence report a sensation of vertigo, a dizziness born not from heights but from scale. The mind, accustomed to framing the universe as a gallery of galaxies, struggles to reconcile with an expanse where all familiar markers vanish. It is a cosmic silence so total that it presses against the psyche, making even seasoned researchers pause, reflect, and whisper in awe at the void's magnitude. Fringe theorists have seized upon this unease, proposing outlandish ideas, portals to other universes, ancient footprints of extraterrestrial civilizations using incomprehensible technology, or regions where the very fabric of physical law fluctuates. While these ideas hover on the edge of scientific respectability, they echo an undeniable truth. The Bootes void provokes questions that stretch far beyond astrophysics, reaching into philosophy, existence, and the nature of nothingness itself. Yet, beneath all this speculation lies a simple, inescapable reality. In the great cartography of the cosmos, there exists a hollow where the galaxies should be, a hole so vast it bends not just light but human understanding. The measurement of such emptiness teaches humility. It reminds us that the universe is neither uniform nor predictable, that amidst the grand symphony of cosmic creation, silence plays its own haunting melody, and as we chart the contours of this vast abyss, we are reminded that sometimes what is missing tells us more than what is present. But within this great emptiness, a question remains unanswered. What of the survivors? What of the 8 flickering lights that defy the darkness? Our next step leads us to these cosmic orphans, galaxies that drift alone, encased in the loneliest region of space. Drifting now, deeper into the void, we find ourselves among the loneliest wanderers in the cosmos. Against the overwhelming blackness, 8 fragile embers flicker, their light stretched thin by unimaginable distances. They are not surrounded by bustling cosmic neighborhoods nor tethered to majestic galactic clusters. Instead, these galaxies hang in isolation, suspended like forgotten lanterns in an endless ocean of night. They are called the void galaxies, the solitary sentinels of the Bootes void, and their existence raises questions even more profound than the emptiness that surrounds them. By all rights, these galaxies should not be here. In a universe governed by the clustering nature of gravity, where matter draws in more matter, creating spirals, clusters, and filaments, the presence of galaxies within a realm almost entirely devoid of structure is a puzzle that both defies statistical expectation and ignites curiosity. These 8 galaxies are like solitary outposts on the fringe of reality, survivors in a wasteland that was never meant to host life, light, or cosmic complexity. Their positions, mapped meticulously by astronomers, are scattered but peculiar. They do not drift aimlessly, rather they seem to form a delicate alignment, whispering of hidden structures beneath the surface of the void. But their rarity alone compels attention. According to cosmological models, a region the size of the Bootes void should contain at least 2,000 luminous galaxies, vibrant with the fusion of countless stars. Yet here, there are only 8, fewer than the number of planets circling our tiny star, fewer than the fingers on our hands. To comprehend their predicament, imagine walking into a concert hall designed to hold thousands, only to find a handful of quiet souls scattered among the vacant seats. The silence is not just auditory, it is spatial, physical, an emptiness so deep it settles into the bones. These galaxies exist within such a silence. Their closest neighbours tens of millions of light years away. The nearest galaxy to Earth, Andromeda, lies a mere 2 million light years from us, a close neighbour by cosmic standards. But these void galaxies endure separation, 20, sometimes 30 times greater. They are, by every measure, cosmic hermit. They bear the scars of their isolation. Many are smaller and dimmer than typical galaxies, their spiral arms less pronounced, their cores less active, their star formation rates sluggish, in the absence of neighbouring galaxies to interact with, to collide, merge, and share matter. These galaxies have aged differently, like children raised in isolation. Missing the developmental pushes and pulls of social interplay, spectroscopic studies reveal more peculiarities. Their stellar populations are poor in heavy elements, the fingerprints of previous generations of star birth and death. In cosmology, we call this metallicity, and it serves as a record of a galaxy's life story. Low metallicity, in these void galaxies, suggests they have formed fewer stars over their lifetimes, perhaps because their isolated environment lacks the raw materials to fuel the stellar nurseries that populate more crowded corners of the universe. Even their movements betray the influence of the void. Unlike galaxies within the dense filaments which are gravitationally tugged in complex dances by their neighbours, the void galaxies move with a tranquil lethargy, floating along paths less disturbed by the tides of mass and gravity. Their velocities are more aligned, more synchronized, as if they drift together along a silent current flowing through the abyss. Curiously, despite their dimness and dormancy, some of these galaxies show hints of resilience. A few exhibit weak star formation, a quiet defiance against their sterile surroundings. Like stubborn flickers of life in a desert, they gather what little gas and dust they can, compressing it into new stars, though the rates are meagre compared to their bustling cousins in denser environments. To peer at them through our telescopes is to witness cosmic endurance. Their light has travelled hundreds of millions of years to reach us, each photon surviving the vast, cold journey through the most barren stretch of space. By the time it arrives at our detectors, it has been stretched, reddened, and weakened, yet it endures, a testimony to persistence in the face of desolation. Fringe thinkers, always eager to probe the mysterious, have wondered aloud, could these galaxies hold secrets unknown to us? Could their isolation have preserved primordial conditions untouched by the interactions and mergers that so often erase the early history of galaxies? Could they be relics of an earlier universe, time capsules carrying the chemistry and structure of a forgotten cosmic era? Mainstream science treads more cautiously, but remains captivated. The survival of these galaxies in a region so devoid of matter suggests there are hidden dynamics at play. Perhaps beneath the observable emptiness lies a filament of dark matter, faint but sufficient to shepherd these galaxies together. Perhaps they are the last remnants of a once denser region, now evacuated by the relentless expansion of the void, stranded like mountaintop villages after a flood. An unsettling question lingers. Are these 8 the last? Are they the final candles burning in a chamber of infinite darkness? As the Bootes void expands, faster than the average cosmic rate, will they eventually be swallowed whole, their light red-shifted into oblivion, their matter dispersed by the silent force that governs the void's hunger. In contemplating them, we glimpse our own fate mirrored in miniature. For our universe, too, is expanding. Dark energy stretches space itself, accelerating the separation of galaxies. In billions of years, the cosmos may look much like the Bootes void, with only isolated islands of stars flickering in an ocean of black. These 8 galaxies stand as both anomaly and prophecy, a vision of the future written in the language of isolation. And so, we drift with them a while longer, observing their quiet glow, listening to the absence that surrounds them, before moving onward, for deeper within the Bootes void lies an even stranger mystery, the impossible symmetry of their arrangement, not scattered chaotically as one might expect, but aligned, stretched along an invisible filament that should not be. The next step of our journey carries us into this strange alignment, into the geometry of nothingness where even in absence, patterns emerge to defy understanding. Within the unbroken silence of the Bootes void, these 8 galaxies remain suspended like fragile jewels in a crown of darkness. They are not merely distant, they are orphaned, raised in the loneliest sector of the known universe. As we approach them more closely, we begin to notice something strange. They do not merely exist in emptiness, they have been shaped by it. Their bones, their breath, their very light carries the imprint of abandonment, moulded not by cosmic kinship, but by exile. In most places in the cosmos, galaxies are born into bustling neighborhoods. They are crowded into clusters, pressed along filaments, pulled into the gravitational embrace of cosmic structures. There, they are constantly engaged in gravitational duels, drawn into collisions, exchanges and violent mergers. They gorge on neighboring gas, rip apart weaker companions, and blossom into grand spirals or colossal ellipticals. Star formation thrives in these energetic crucibles where galaxies interact like a vibrant, competitive ecosystem. But here, in the void, these processes falter. The galaxies are too far apart to exert meaningful influence on each other. Their dance partners are absent, their playmates distant. They drift along inertial paths, mostly untouched by the chaos and creativity that fuels the growth of galaxies in denser regions. And like any living thing raised in isolation, they have grown different. The first peculiarity lies in their star formation. Studies show that these void galaxies birth stars at a rate drastically lower than their counterparts in galactic clusters. Star formation is not merely slowed, it is stifled, choked by the scarcity of raw material. Without the constant inflow of fresh gas, without the collisions that compress molecular clouds into birthing grounds for stars, these galaxies have grown old before their time. Their starlight is cooler, redder, populated by aging stellar populations, rather than the brilliant blue of youthful starbursts. Spectroscopy reveals the chemical fingerprints of this arrested development. In richer galactic environments, each generation of stars enriches the interstellar medium with heavier elements, carbon, oxygen, iron, forged in the heart of massive stars and expelled in supernovae. These heavy elements, called metals in astronomical parlance, are essential for forming planets, for cooling gas clouds, for nurturing complexity. Yet in the void, these 8 galaxies show a striking poverty of metals. Their metallicity is anomalously low, suggesting they have experienced fewer cycles of star birth and death, fewer generations to enrich their surroundings. They are in a sense primordial, echoes of an earlier universe where the first stars struggled to light up a cold, dark cosmos. Some of these galaxies resemble dwarf galaxies, smaller and dimmer than typical spirals or ellipticals, with irregular shapes and patchy structures. Others maintain a whisper of spiral arms, but these spirals are subdued, pale sketches compared to the majestic swirls of galaxies like the Milky Way. Astronomers have long known that environment shapes the destiny of galaxies. This phenomenon, called the morphology-density relation, shows that galaxies in crowded environments tend to become ellipticals, losing their gas in violent interactions, ceasing star formation. Conversely, galaxies in less dense environments retain their gas and their spiral structures longer. Yet the void galaxies fall outside even these norms. They are too quiet, too chemically simple, too underdeveloped. Their lives, it seems, have been suffocated not by violence but by isolation. There is more. Their motions reveal another layer of strangeness. In typical cosmic regions, galaxy velocities are chaotic, pulled and accelerated in all directions by the gravitational tug-of-war between countless neighbours. Yet within the Bootes void, the galaxies appear to be moving in smoother, more aligned paths, as though they share a common flow. Some cosmologists describe this as a laminar motion, a gentle, unified drift through space, lacking the turbulence seen elsewhere. This raises questions that challenge conventional cosmology. Why are these galaxies aligned in motion? What hidden structure guides them along these coherent paths? Could there be invisible threads of dark matter too diffuse to trigger normal galaxy formation, yet sufficient to shepherd these few survivors through the void? One speculative idea suggests that these galaxies mark the ghostly remnants of a long-dispersed filament, the once vibrant bridge of matter, now stretched thin by the expanding void. What remains are mere relics, cosmic fossils drifting along the faded footprint of structure. Another proposal points toward the idea of fossil void galaxies, systems that formed before the void took shape, left behind as emptiness consumed the surrounding regions, stranded on diminishing islands of matter. Computer simulations provide conflicting insights. Some models can replicate void galaxies under specific initial conditions, but few can fully explain the stark contrast in metallicity, structure, and star formation rates. The probability of galaxies forming, surviving, and remaining so isolated over billions of years in such a vast underdense region remains extremely low. Statistically, their existence is a cosmic improbability. Yet the void galaxies persist. They invite the notion that there may be forms of galactic evolution that do not conform to our current paradigms, pathways shaped by the absence of interaction rather than its abundance. Could such isolation preserve ancient galactic features lost in more crowded environments? Might these galaxies contain clues to the earliest epochs of the universe, untouched by the gravitational sculpting that has transformed so much of the observable cosmos? Fringe theories, unproven but irresistibly provocative, propose even wilder possibilities. Could the low metallicity indicate that these galaxies are composed of exotic forms of matter, resistant to standard chemical evolution? Could they harbour an altered dark matter composition, or interact with dark energy in a way unknown to standard physics? Some even speculate whether the isolation of these galaxies makes them candidates for hosting forms of life or civilization fundamentally different from those in denser, more chaotic cosmic regions, worlds shaped by eons of quietude, undisturbed by the gravitational upheavals of galactic collisions. We do not have the answers. What we have are the faint, trembling lights of these 8 survivors, straining to reach us across hundreds of millions of light years. Their existence speaks of resilience, of the universe's ability to sustain complexity even in the most barren of cradles. Yet, as we drift onward, the landscape shifts. For these galaxies, isolated as they are, do not lie in random positions. They arrange themselves in an improbable order, forming a line, a tube, a structure that defies chance. In a void where chaos should reign supreme, we find precision geometry, an unseen hand guiding matter into alignment. Next, we follow this invisible filament, this cosmic string threading through the emptiness, into a formation that raises even more profound questions about the underlying architecture of our universe. Within the heart of the Bootes void, where emptiness reigns supreme and matter has seemingly surrendered to the infinite dark, the 8 galaxies are not scattered like debris adrift in chaos. No, they are arranged, stretched, aligned along a mysterious path, as though some unseen architect traced a faint line through the abyss and positioned these isolated beacons along it. It is a filament, a ghostly thread, a cosmic tube threading through the void, where structure should by all accounts be absent, and it defies every natural expectation. This arrangement was first noticed by astronomers as they meticulously plotted the positions of these rare survivors. Galaxies, by their nature, tend to cluster. They form clumps, groups, arcs, and walls drawn together by the fundamental pull of gravity. In voids, by definition, such clustering is erased, leaving only sparse, disconnected wanderers. But the galaxies within Bootes do not obey this rule. They appear to form a slender line, a tubular alignment stretching for tens of millions of light years across the vast emptiness, as though following the ghostly imprint of an ancient, forgotten pathway. The discovery of this alignment stunned cosmologists. Statistically, such an arrangement is wildly improbable. When simulations of voids are run, feeding supercomputers with the physics of cosmic evolution, gravitational dynamics, and dark matter distribution, they yield void galaxies, but these are scattered, drifting without coherent order. The neatness of the Buttigieg tube, as some call it, emerged as a distinct anomaly. Scientists questioned their data. They cross-verified with multiple surveys, peered through radio telescopes and optical instruments, and applied statistical rigor to the discovery. The conclusion was unavoidable. This was no observational artifact, no accidental clustering of data points. There, within the void's deepest hollows, galaxies had formed, aligned in a configuration that resisted easy explanation. So how could such an alignment form within one of the emptiest places in the universe? Some astronomers look to the large-scale structure of the cosmos for answers. The cosmic web, after all, is built of filaments, long thread-like regions where galaxies and matter are drawn together along gravitational ridges. These filaments feed galaxy clusters, streaming matter into the nodes of the cosmic web like vast rivers draining into lakes. Could the Buttigieg tube be the faded remnant of such a filament, a skeletal structure left behind as the surrounding matter was evacuated? It is a tempting theory, but it faces a problem. Most voids do not contain coherent filaments. Where matter density falls below a critical threshold, the filamentary architecture collapses, matter stops accreting, gravitational wells flatten out, and structure disintegrates into scattered remnants. Buttigieg, being one of the most extreme voids, should be devoid of such filamentary remnants. And yet, the alignment persists, as though some underlying skeleton still guides the galaxies through the dark. Dark matter emerges, once again, as a suspect. Though invisible, dark matter exerts a gravitational pull, shaping the scaffolding upon which galaxies are formed. Perhaps, deep within Buttigieg, an ultra-faint dark matter filament survives, too diffuse to gather enough baryonic matter to form typical galaxies, but sufficient to anchor these few survivors in a fragile alignment. Observational efforts to detect gravitational lensing, a method to infer the presence of dark matter through its bending of light, are underway, though results remain inconclusive. Other researchers have proposed that this alignment may be a fossil remnant of the early universe. During the epoch of recombination, when the universe cooled enough for light to travel freely, tiny quantum fluctuations seeded the distribution of matter. Over billions of years, these ripples evolved into the web of galaxies we see today. Perhaps, in the unique environment of Buttigieg, one such fluctuation persisted as a thin, weak filament, forming just enough overdensities to birth these few galaxies along its spine, even as the surrounding regions remained empty. A more speculative, but no less fascinating proposition considers cosmic expansion itself. The universe is not merely expanding, but accelerating, driven by the enigmatic force of dark energy. Some cosmologists have wondered if local variations in the strength of dark energy could create stretch marks in the cosmic fabric, regions where expansion was uneven, sculpting unusual void structures like elongated filaments even within vast emptiness. If true, the Buttigieg tube could be a manifestation of exotic dark energy dynamics, hinting at underlying physics we have yet to comprehend. Fringe theories drift into more provocative territory. Some theorists working on the speculative edge of cosmology have proposed that such structures could be imprints from interactions with other universes, a byproduct of cosmic collisions in a multiverse scenario. In this view, the alignment of galaxies is a scar from a brush with an adjacent universe, an ancient ripple where the physics of two realms intersected briefly before parting. Mainstream science remains cautious, but such theories, while unproven, capture the imagination, inviting us to consider realities far beyond our own. Regardless of origin, the Buttigieg tube poses uncomfortable questions. If such alignments exist in one void, do they exist in others? Are they simply overlooked, hidden by the limitations of our surveys? Or is Buttigieg uniquely scarred, holding secrets not mirrored elsewhere in the cosmos? Attempts to answer these questions have led astronomers to scan other voids, searching for similar alignments. Preliminary results suggest occasional filamentary structures within smaller voids, but none rival the size, coherence, and improbability of the Buttigieg tube. It remains unique, a singular example of improbable order thriving within vast disorder. Its implications extend beyond structural curiosity. Galaxy evolution, it seems, is not solely determined by environmental density. but also by these faint, hidden geometries. The galaxies along the Buta's tube, despite their isolation, may experience mutual gravitational interactions over unfathomably long timescales, subtly influencing their evolution, rotation curves, and internal dynamics. Their chemical compositions may differ along the alignment's length, reflecting minute differences in the underlying dark matter distribution. This cosmic tube forces a re-evaluation of our assumptions about void environments. It suggests that voids are not simply empty, they are textured, structured in ways subtle enough to evade casual detection, but profound enough to shape the destinies of the galaxies within them. And beyond these scientific revelations lies something deeper, a sense of awe. There, in the most barren region of the known universe, where chaos and emptiness should prevail, we find symmetry, order, and structure. It whispers of a universe that is not merely random but poetic, where even in desolation patterns persist and in the silence, unseen hands weave intricate designs. As we trace this alignment through the void, we begin to sense its dynamic nature, for this is not a static scar. It is expanding, stretching further apart as the void itself grows. The Boots tube is a transient structure, a fleeting arrangement, destined to dissolve in the accelerating future of the universe. Ahead lies the revelation of the void's hunger, the knowledge that this emptiness is not passive, but actively consuming, growing faster than the universe itself. The next step in our journey pulls us into the creeping expansion of the Bootes void, and the unsettling realization that even nothingness has an appetite. Step further into the silence, and you will feel it, a subtle but relentless expansion pressing against the boundaries of existence. The Bootes void is not a static absence carved long ago and left to linger unchanged in the tapestry of the universe. It is alive in its own chilling way, stretching outward, consuming more of the cosmos, swallowing light, matter, and structure in a quiet, unceasing hunger. This void, this gaping emptiness, is growing, expanding at a rate that outpaces the average rhythm of the universe itself. This revelation did not come quickly. For many years after its discovery, astronomers assumed the Bootes void, like other cosmic voids, was a relic of ancient cosmic evolution, a leftover feature from the chaotic aftermath of the Big Bang. But as telescopes sharpened their gaze and cosmological surveys mapped the distribution of galaxies with finer precision, a disturbing trend emerged. The galaxies at the edge of the void were moving not just because of the general cosmic expansion, but seemingly pushed, repelled, as though the void itself were actively clearing out space. Measurements of galaxy velocities surrounding the void revealed an unexpected signature. Galaxies on the periphery were not only receding from us as expected by the Hubble expansion, but also accelerating away from the center of the Bootes void at a rate exceeding the standard cosmic flow. It was as if the void was inflating, stretching its invisible walls outward faster than the rest of space. This local expansion rate, approximately 10% faster than the Hubble flow, defied standard models. What could cause such an acceleration? Nestled within an already expanding universe, gravity, the master sculptor of cosmic structure, operates by pulling. Matter attracts matter, forming stars, galaxies, clusters, and webs. But here we encounter a counterforce, a phenomenon where galaxies are effectively pushed outward, as though repelled by an unseen hand. This is the hallmark behavior of a void, but in Bootes, it is magnified to an extreme, suggesting that voids are not merely passive scars in the cosmic web, but dynamic players in the evolution of the universe's structure. One explanation lies in the basic physics of underdense regions. In the standard model of cosmology, regions with less matter experience weaker gravitational pull. As the rest of the universe clumps and collapses into dense structures, the low-density zones, the voids, are left behind, expanding more rapidly in relative terms. Matter flows outwards, from emptiness into structure, leaving the void to balloon, widening the chasm between galaxies. In Bootes, this natural behavior seems amplified, as though the void's starting conditions were even more extreme, or its internal dynamics more complex. Perhaps it was seeded by an unusually deep primordial underdensity during the earliest epochs, causing it to grow faster and more aggressively than typical voids. Or perhaps hidden forces, like variations in dark energy density, play a role in enhancing its expansion. Indeed, some cosmologists have considered whether the Bootes void represents a local fluctuation in dark energy. If dark energy, the mysterious driver of the universe's accelerating expansion, is not uniformly distributed, then regions like Bhuta's could act as zones of intensified repulsion, where space itself stretches faster, tearing galaxies away from each other more violently than elsewhere. Observational evidence remains elusive, but such hypotheses push the frontier of theoretical cosmology, hinting that the void may be a window into unknown physics. Another layer of complexity is added by the surrounding structures. The Bhuta's void does not exist in isolation. It is bounded by dense walls of galaxies, massive filaments that mark the transition from emptiness to overabundance. These regions exert their own gravitational pull, further encouraging matter to drain away from the void's heart and accumulate along its periphery. This interplay, the internal repulsion of the void, combined with the external attraction of dense walls, creates a feedback loop that accelerates the clearing out of the void, feeding its expansion like a growing storm. Some researchers have begun to model void dynamics as an emergent property of large-scale cosmic flows. In this framework, voids are not merely passive gaps, but active zones that evolve dynamically, influencing the movement of galaxies, bending light, and contributing to the anisotropy of cosmic expansion. The Bhuta's void, in particular, may serve as a natural laboratory for studying these effects, offering insights into how emptiness itself can shape the fate of the universe. This growing hunger of the void holds unsettling implications for the distant future of cosmic evolution. As the universe continues to expand, driven by the relentless push of dark energy, voids like Bhuta's will grow larger, their walls retreating, their interiors becoming increasingly barren. The few surviving galaxies within them will drift further apart, their light red shifted into oblivion, until they vanish beyond detectability. The Bhuta's void, colossal as it is today, may be but a glimpse of the universe's ultimate destiny, a future where vast, dark, empty spaces dominate, and islands of light become vanishingly rare. Some astrophysicists predict that in 100 billion years, galaxies will be so isolated that their light will never reach other civilizations, and the observable universe will shrink to a lonely bubble of local matter surrounded by infinite blackness. The Bhuta's void then is not just a current oddity but a prophecy written in space, showing us what is to come, a universe retreating into itself, hollowing out, until existence is defined more by absence than presence. This expanding void also offers a profound reflection on the balance of forces that govern reality. Where gravity gathers and binds, the void disperses and isolates. Where stars burn and galaxies cluster, emptiness stretches and separates. Together they compose the symphony of the cosmos, creation and erosion, clustering and expansion, presence and absence, dancing across billions of light years. There is an eerie beauty in this duality. The Bhuta's void teaches us that not all forces are about accumulation and growth. Some forces erase, scatter, and hollow out the universe, leaving behind silence so complete that it humbles human imagination. In understanding the void's hunger, we come to appreciate the fragile, transient nature of cosmic structure, the fleeting presence of stars and galaxies in a universe destined for ever-expanding emptiness. And yet, even within this encroaching darkness, structure persists along the periphery. Great walls of galaxies, dense and vibrant, form boundaries where light and matter gather in defiance of the void's consumption. These cosmic ramparts are the next frontier, the battleground where the opposing forces of emptiness and clustering collide. Our journey now drifts to these walls, to the dense, crowded regions that stand like ancient fortresses along the edge of the abyss. Here, galaxies throng together, resisting the pull of the void, compressing into grand formations that hold back the advancing darkness. For now, at the threshold where emptiness ends and existence begins, there stands a barrier, a vast luminous barricade of matter known as the Void Wall. Here at the outskirts of the Bhuta's void, the universe gathers its defenses, concentrating galaxies, clusters and filaments into colossal structures that rise like mountains from a barren plain. While the center of the Bhuta's void is haunting in its absence, its borders throb with density, with gravity, with light, an awe-inspiring reminder that even in a universe governed by entropy and dispersion, there are places where matter fights back. As we drift to the boundary, we are met with a dramatic transformation. The deafening silence of the void gives way to a cosmic symphony of motion and mass. Galaxies, once distant and solitary within the emptiness, appear by the hundreds, then thousands, clustering together in complex formations. In these walls, matter is compressed by the outward push of the void, and the inward pull of surrounding structures, creating some of the densest known configurations of galaxies in the observable universe. The transition is not gradual, it is sudden, abrupt, a sharp gradient from near-total emptiness to overwhelming abundance, where the density of galaxies can increase by factors of hundreds within a span of mere tens of millions of light-years. This stark divide is one of the defining features of voids, and in Bootis it is especially dramatic, like crossing from the depths of an abyss straight into a bustling metropolis of stars. These void walls are not merely collections of galaxies, they are intricate, dynamic networks of cosmic architecture. Filaments twist through them like strands in a colossal web, connecting superclusters and bridging vast distances. Clusters of galaxies, some containing thousands of individual systems, huddle along these threads, their gravitational fields warping space, their light beaming across the ages. The Hercules supercluster is one such giant stationed at the edge of the Bootis void. It stands as a titanic guardian, comprising multiple rich galaxy clusters entwined in a gravitational embrace. Galaxies within Hercules spin and collide, merge and consume, growing in mass and brilliance even as the void behind them expands. The juxtaposition is striking. Within a short cosmic distance, the universe transitions from the loneliest desert to one of the most crowded galactic gatherings known. Astrophysicists have long studied these walls to understand the mechanics of large-scale structure formation. Simulations reveal that voids, by expelling matter, act as architects of these walls, driving galaxies outward until they accumulate along the boundary. It is a phenomenon akin to the shores of an ancient cosmic ocean, where waves of gravity crash, piling matter into ridges that define the limits of emptiness. But these walls are not static monuments. They are alive with motion, with the ceaseless flux of galactic migration. Galaxies along the wall are often subject to intense gravitational interactions. Close encounters and full-blown collisions are common, triggering bursts of star formation, igniting central supermassive black holes, and shaping galaxies into new forms. Spiral galaxies, rich with gas and ongoing stellar births, frequently merge and metamorphose into massive ellipticals, their chaotic pasts etched into their diffuse halos. A striking example of this dynamic interplay is the Coma cluster, located near the Bootis boundary. It is a dense, violent congregation of over 1,000 galaxies, dominated by ancient elliptical giants. Within its confines, the motions are frenetic. Galaxies hurtle through the cluster at breakneck speeds, drawn inexorably toward the cluster's dense core. The environment is inhospitable to gas retention. Hot plasma permeates the cluster, stripping galaxies of their star-forming material and accelerating their evolution toward dormant red, featureless forms. This intense clustering has profound effects on the galaxy's life cycles. Galaxies along the void wall age rapidly compared to their isolated counterparts. The rate of galactic cannibalism, where large galaxies consume smaller neighbors, is significantly higher, leading to the formation of ultra-massive galaxies, some of the largest in the known universe. These ancient titans, with central black holes billions of times more massive than our Sun, dominate the gravitational landscape, exerting influence over their entire neighborhood. The Bootis void, through its expansion, plays an active role in feeding these walls. As galaxies drift away from the center of the void, they are funneled toward these dense peripheries, like water flowing downhill into basins. This flow, known as void evacuation, contributes to the growth of the surrounding structures, making void walls not merely static leftovers, but actively evolving systems that grow denser over cosmic time. Intriguingly, this process creates observable asymmetries. The side of the void adjacent to a major supercluster will often show denser, thicker walls, while regions opposite may remain thinner or less structured. The Bootis void itself displays such asymmetries, with denser filaments forming near the Hercules and Coma superclusters, while other regions of its boundary remain relatively sparse. These irregularities provide crucial insights into the gravitational landscape of the cosmos, revealing how voids and clusters co-evolve. Yet, beyond the gravitational mechanics, the void walls also serve as natural laboratories for studying galaxy transformation. Within them, we can observe galaxies in all stages of evolution, from youthful, gas-rich spirals to ancient quiescent ellipticals, offering a unique cross-section of cosmic history. The accelerated interactions here allow scientists to study processes that in less crowded environments would take much longer to unfold. A curious byproduct of this environment is the phenomenon of backsplash galaxies, systems that are ventured into the dense interior of a cluster endured violent gravitational encounters, and been flung back out toward the void's edge. These galaxies, carrying scars from their interactions, retain traces of their high-density journey despite now residing in the quieter outskirts. Their discovery adds layers of complexity to our understanding of galaxy distribution and evolutionary history along void walls. Even stranger is the influence of the void on the temperature and flow of intergalactic gas. Surveys using X-ray and radio observations reveal that the walls around Bootis are not only sites of galactic accumulation but also reservoirs of hot plasma, flowing rivers of ionized gas, and shock fronts where void expansion meets resistance. These regions glow faintly in X-ray wavelengths, their thermal signatures mapping the hidden currents of energy sculpting the cosmic web. Some theorists speculate that these zones of compression could harbour rare astrophysical phenomena, from amplified magnetic fields to enhanced particle acceleration, possibly contributing to the mysterious ultra-high energy cosmic rays detected on Earth. Though speculative, the interplay between void dynamics and energetic processes at the walls remains a fertile ground for future discovery. At a grander scale, these walls help us understand the broader fate of structure in the accelerating universe. As voids grow and walls thicken, the universe becomes increasingly fragmented into isolated clusters and superclusters, surrounded by ever-expanding seas of emptiness. The long-term outlook suggests that only these dense walls will remain as beacons of matter, while the spaces between grow colder, darker, and more silent. Thus, the Boot void is more than an expanse of absence. It is a force of change, reshaping the peripheries of the universe into brilliant, crowded bastions of light. Where there is emptiness, there is also abundance. Where there is dispersal, there is clustering, locked in an eternal balance across the cosmos. As we prepare to leave the turbulent borders and plunge back toward the void's interior, we find ourselves contemplating a stranger force at work: gravity's twisted reflection, the subtle push of anti-gravity within the void, shaping not only the trajectories of galaxies but the very rhythm of space-time itself. It is here in the deepest depths of nothingness that the rules of gravity seem to bend, and we will follow their quiet rebellion. Within the cosmic dance, gravity is the tireless sculptor, the force that binds galaxies, forges stars, and weaves the threads of the cosmic web. It is the quiet architect that transformed the raw, chaotic energy of the Big Bang into elegant spirals and luminous clusters. But here, in the hollow heart of the Booter's void, we encounter a place where gravity falters, where its song grows faint, and something stranger seems to take hold, a gentle, persistent repulsion, a phenomenon that scientists have come to call cosmic anti-gravity. At first glance, this notion seems absurd. Gravity only attracts, it is the great gatherer, pulling everything toward everything else. Yet, when astronomers study the velocity flows within and around the Booter's void, they witness an unsettling signature. Galaxies are not simply coasting along with the universal expansion. They are moving away from the void's center at rates faster than the Hubble expansion would predict. It is as if something within the void pushes galaxies outward, creating an additional acceleration, a localized speeding up of cosmic separation. This observation presents a paradox. If the void is a region of lower than average matter density, its gravitational pull should be weaker, yes, but it should not actively repel. The mathematics of general relativity tells us that less matter means less attraction. It does not suggest a reversal of gravitational pull. And yet, in the depths of Bootis, space behaves as if repulsion dominates, as if emptiness itself generates a pushing force. To understand this eerie phenomenon, scientists turned their focus to the underlying nature of cosmic expansion. Since the discovery of the universe's acceleration in the late 1990s, driven by what we call dark energy, it has become clear that the cosmos is expanding at an ever-increasing rate. Dark energy acts as a form of anti-gravity, accelerating the stretching of space, overpowering the binding force of gravity on the largest scales. In voids like Bootis, this repulsive tendency is magnified. With less matter present to exert gravitational influence, the repulsive effect of dark energy is less opposed. Galaxies within the void experience not only the general push of cosmic expansion, but an additional acceleration from the local underdensity, a gravitational deficit that causes them to drift away faster than their counterparts in denser regions. Mathematically, this effect is elegantly described through the concept of gravitational potential. In high-density regions, gravitational potential is deep, pulling objects inward. In voids, the potential is shallow, even positive in extreme cases, effectively creating an environment where galaxies accelerate outward, not because of a mysterious force pushing them, but because of the lack of sufficient gravity to counteract expansion. In essence, emptiness creates a kind of passive repulsion, a natural consequence of uneven cosmic structure in an accelerating universe. This interplay creates a fascinating battlefield at the void's boundaries. On one side, the dense walls and clusters pull galaxies inward with overwhelming gravitational force. On the other, the hollow heart of the void offers only weak attraction, allowing the repulsive pressure of dark energy to dominate. Galaxies near the edge feel a complex gravitational tug-of-war, their trajectories shaped by competing forces, a gravitational ballet choreographed by both presence and absence. Simulations of large-scale structure formation confirm this dynamic. When cosmologists model the evolution of cosmic voids, they observe that voids expand faster than the background universe, pushing matter outward and contributing to the growth of surrounding filaments and walls. This accelerated evacuation reshapes the void over billions of years, stretching its size and thinning the residual matter within. The Buta's void, being one of the largest known, serves as a textbook example of this gravitational imbalance. Interestingly, this anti-gravity effect is not uniform. The distribution of nearby superclusters causes anisotropies in the flow of galaxies. Galaxies situated near prominent walls experience stronger gravitational pulls and slower outward velocities, while those in sparser directions are flung away more rapidly. This results in a subtle drift of the void's center over cosmic time, an ever-shifting heart where the emptiness is most profound. But could there be more than just the absence of gravity at work? Some alternative theories in cosmology have speculated about exotic physics within voids, ideas that flirt with the edges of mainstream science. One proposal suggests that dark energy might not be a uniform field, but could cluster slightly in underdense regions, enhancing the local repulsive force. If true, voids like Botes might be sites where dark energy's influence is amplified, creating more rapid expansion rates within their borders. Another speculative frontier involves the idea of scalar fields, hypothetical fields predicted by certain extensions of general relativity and string theory. These fields, if they exist, could modify gravity's behavior in low-density environments, effectively turning gravity into a repulsive force within vast voids. While no direct evidence exists for such fields, void dynamics offer a tantalizing testing ground for these fringe ideas. Even within the more grounded framework of standard cosmology, the study of voids has led to nuanced discoveries. The integrated Sachs-Wolf effect, a phenomenon where cosmic microwave background CMB photons gain or lose energy when passing through large structures, has been used to measure the imprint of voids on the early universe's radiation. Studies of the Buta's void and similar structures suggest subtle anomalies in the CMB temperature fluctuations, adding weight to the theory that voids play an active role in shaping the cosmic expansion history. One of the most poetic aspects of this gravitational behavior is how it reflects the grand narrative of the universe. In the earliest epochs, gravity reigned supreme, collapsing matter into stars and galaxies, forging the rich structures we see today. But as the universe aged, dark energy's influence grew, and voids like Botes emerged as realms where gravity's influence waned earliest. Where the accelerating expansion took hold more aggressively, they are the frontier outposts in the universe's slow march toward emptiness. When we peer into the Buta's void, we are gazing into the future of the cosmos. The accelerating expansion that dominates here will, in time, permeate everywhere. Galaxies across the universe will drift apart, gravitational bonds will weaken, and the islands of light will be cast adrift in a sea of dark, cold space. The Buta's void offers us a glimpse of that endgame, where repulsion overtakes attraction, where structure unravels, and the universe recedes into silence. Yet, even in this domain where anti-gravity holds sway, there are ripples of defiance. The walls persist, galaxies continue their internal cycles, stars are born, and life perhaps clings to existence in some quiet corner. The contrast is striking, an ever-growing void pressing outward, surrounded by dense, brilliant clusters fighting to hold their form. In the next stage of our journey, we will lift our eyes even higher, beyond the local gravitational fields to an ancient imprint that blankets the entire universe, the faint, echoing glow of the cosmic microwave background. Within it, astronomers have found a chilling anomaly, a cold spot that aligns eerily with the Bhuta's void, suggesting that the fingerprints of this emptiness may stretch back to the dawn of time itself. Lift your gaze beyond the galaxies, past the walls of clustered brilliance, past the rushing escape of galaxies from the Bhuta's void's center, and you will find an even older light, the faint afterglow of creation itself. It is the oldest image in existence, a cosmic photograph imprinted upon the sky, known as the cosmic microwave background, or CMB. This ancient light is the whispered echo of the Big Bang, a frozen memory of a universe just 380,000 years old, stretched and cooled by 13.8 billion years of expansion. It fills the sky in every direction, a faint hiss of energy from a time before stars, before galaxies, before voids. And yet, in this backdrop of ancient uniformity, a scar appears, a colder, quieter spot than anywhere else, a void within the afterglow, aligned uncannily with the Bhuta's void itself. This is the cold spot, a region in the CMB that has puzzled cosmologists for decades. First detected by the Wilkinson Microwave Anisotropy Probe, WMAP, in the early 2000s, and later confirmed by the Planck satellite, the cold spot is a vast area of the sky where the temperature of the cosmic microwave background dips lower than statistical models predict. Across billions of light years, where uniformity should reign, this anomaly stands out, like a bruise on the ancient face of the cosmos. Its coincidence with the Bhuta's void has sparked intense interest. Could the largest known void in the nearby universe have imprinted itself upon the oldest light we can observe? Could the immense emptiness stretching hundreds of millions of light years across cause a ripple in the fabric of space-time so vast it reaches back into the earliest moments of creation? To answer this, we must understand how voids interact with light. Photons from the cosmic microwave background have been journeying across the universe since the dawn of time, crossing the ever-shifting landscape of cosmic structure. When these photons pass through large gravitational wells like superclusters, they gain energy falling into the gravitational potential and lose it climbing back out. In regions of relatively constant gravitational potential, this energy exchange cancels out. But voids like Bhuta's complicate this picture. In an accelerating universe dominated by dark energy, the gravitational potential inside voids changes as photons traverse them. As photons enter a void, they lose energy, entering the shallower gravitational well. But because the void expands and grows during their journey, the well becomes even shallower by the time they exit. The photons fail to regain their lost energy, exiting colder than when they entered. This is the integrated Sachs-Wolf ISW effect, a subtle shift in the energy of ancient photons caused by evolving gravitational structures. In the case of the Bhuta's void, the effect is magnified. The void's sheer scale, combined with its enhanced local expansion rate, can cause a more significant energy loss, leaving an imprint on the CMB in the form of a cold region. This theory offers an elegant explanation. The cold spot is not a primordial feature, but a shadow cast by the Bhuta's void, a lingering trace of cosmic emptiness projected onto the light of creation. Yet, even with this compelling model, questions linger. The cold spot's size and temperature dip are larger and deeper than most simulations predict. Even accounting for the Bhuta's void, alternative analyses suggest that the void could only account for a portion of the cold spot's anomaly, implying that other factors may be at play. Could multiple voids along the line of sight be contributing? Or could the cold spot be a composite of multiple astrophysical effects? More provocatively, some cosmologists have wondered whether the cold spot hints at new physics beyond the standard model of cosmology. In speculative corners of theoretical physics, ideas abound. Perhaps the cold spot is the scar of a primordial defect, a relic from an early cosmic phase transition, a cosmic string or a domain wall left from the universe's infancy. Others propose even more radical possibilities. The cold spot is the bruised edge of our universe after colliding with another bubble in a multiverse scenario, a place where the fabric of reality brushed against a neighboring cosmos. These ideas remain unproven, and mainstream consensus holds that the ISW effect from voids like Bhuta's likely explains at least part of the cold spot's signature. Observations of similar but smaller voids have shown corresponding, though less dramatic, temperature decrements in the CMB, reinforcing the link between cosmic emptiness and cold shadows on the sky. The significance of this alignment extends beyond solving a single anomaly. It reveals the profound connectedness of the universe across unimaginable distances and timescales. Here we stand, billions of years after the Big Bang, observing ancient photons that have traversed the entirety of cosmic history, their energy subtly altered by structures that did not exist when they began their journey. The Bootes void, a relatively young structure in cosmic terms, whispers its presence across the gulf of time, leaving fingerprints on the oldest light in existence. This interplay between structure and background between now and then underscores a fundamental truth about the universe. It is not a static backdrop, but a living, evolving entity, where the past and present are woven together in delicate, measurable ways. The Bootes void is more than an empty space. It is a lens through which we can study the unfolding of cosmic expansion, the behavior of dark energy, and the fine-scale structure of space-time itself. Modern observational campaigns continue to refine these measurements. Radio telescopes and next-generation cosmic surveys aim to map the distribution of voids with greater precision, to trace their effects on the CMB and large-scale flows of galaxies. Scientists hope that by cataloguing these shadows in the microwave background, we can piece together a clearer image of the universe's acceleration, test the properties of dark energy, and probe the validity of cosmological models. And perhaps through these studies we will approach answers to the deeper mysteries. Why does the universe accelerate? Why is dark energy so dominant? Why do voids grow at such extraordinary rates? The cold spot, in its quiet anomaly, may yet unlock secrets about the birth and fate of the cosmos. As we leave the ancient light behind and return to the silent depths of the Bootes void, another mystery emerges. If voids like Bootes leave such imprints on the universe's oldest light, what of the dark components of the universe themselves? Do voids influence not only visible matter but the elusive, invisible web of dark matter that underpins all structure? And more curiously, can even dark matter flee from emptiness? Our path now guides us into the unseen, into the shadows where dark matter should lie, abundant, but in the Bootes void appears curiously absent. It is a journey into the hidden backbone of the cosmos, and into the startling question, what happens when even the invisible dares not linger? In the theatre of the cosmos, dark matter is the invisible scaffolding upon which galaxies are built, the unseen architect, whose silent pull binds the luminous universe into its intricate lace-like patterns. Though it neither emits nor absorbs light, its gravitational influence sculpts everything from the smallest dwarf galaxies to the grandest superclusters. It is thought to account for more than 5 times the mass of all the ordinary matter we can see, threading the vis with filaments of invisible mass. And yet, within the Bootes void, a curious enigma emerges. Even this silent, omnipresent force appears to be absent, withdrawn, avoiding the hollow heart of the void. This absence is unsettling because, according to the prevailing models of cosmic evolution, dark matter should be everywhere, permeating space even in the loneliest regions. While galaxies are expected to be sparse within voids, the dark matter that birthed those galaxies is thought to extend throughout the universe, forming a delicate web that underlies all visible structures. Yet, when astronomers study the Bootes void, they encounter a contradiction. Not only is visible matter scarce, but the gravitational signatures suggest that dark matter too is dramatically underrepresented, making the void even emptier than models would withered. Detecting dark matter is a formidable challenge. We cannot see it directly, but we can infer its presence through its gravitational effects on galaxies and light. One of the most powerful tools in this quest is gravitational lensing, the bending of light from distant galaxies by the mass of intervening structures. In regions rich with dark matter, gravitational lensing distorts and magnifies background galaxies, leaving telltale warps in their appearance. Yet, when astronomers peer through the Bootes void, these distortions weaken, nearly vanish, confirming the deep underdensity not just in visible light but in the hidden mass itself. This phenomenon is referred to as a supervoid, an area devoid of both baryonic matter, the normal atoms that make up stars and planets, and dark matter alike. The Bootes void is one of the most extreme supervoids known, a desert of matter in all its forms, stretching 330 million light-years across. It is not merely a gap in the starry expanse, but a wound in the invisible cosmic web, a place where the universe's most fundamental scaffolding thins to a whisper. Why would dark matter, which is supposed to be the primal force behind structure formation, retreat from such a vast region. Some cosmologists propose that this is simply the statistical tale of natural cosmic variance, that in the grand lottery of the early universe, fluctuations in the density field created rare extreme underdensities like bootas, emptying even dark matter through gravitational migration. In this view, the absence of dark matter in the void is a product of early conditions, amplified by billions of years of cosmic evolution as matter streamed away toward denser regions, feeding the growth of clusters and leaving behind a gravitational hollow. Others suggest more nuanced mechanisms. Simulations indicate that as voids expand and mature, their gravitational fields can actively repel matter, a process called void evacuation. In these regions, the cumulative push of surrounding overdensities can siphon both normal and dark matter toward the peripheries, thinning the internal density to levels far below the cosmic average. Bootus, as the largest of these voids, represents an extreme endpoint of this process, a place where gravitational evacuation has run nearly to completion. However, some anomalies persist. Even the most advanced cosmological simulations struggle to produce voids as empty as Bootus, particularly in terms of dark matter depletion. While significant underdensities are common, the sheer scale and depth of the Bootus void remains difficult to reconcile with standard models. This has led some researchers to propose that voids might serve as sensitive probes for new physics, windows into aspects of cosmology that remain hidden in denser regions. One speculative avenue explores the possibility that dark matter itself may have multiple components, some that cluster strongly under gravity, and others that interact differently, perhaps being more susceptible to dark energy's repulsive influence. If certain forms of dark matter interact weakly, even with gravity, they might evacuate voids more readily, explaining the extreme emptiness of Bootos. While such models remain highly conjectural, the Bootos void offers a unique laboratory to test these radical possibilities. Other theories consider the potential role of dark energy fluctuations. Though dark energy is typically modeled as a uniform field, alternative frameworks suggest it might clump or vary subtly across vast distances. If the Bootos void is a region of elevated dark energy density, this could explain both its accelerated local expansion and the anomalously low presence of both visible and dark matter. Current observations lack the sensitivity to confirm or refute this, but future cosmic surveys may reveal whether dark energy's influence is truly uniform or conceals hidden structures of its own. Beyond physics, the absence of dark matter within Bootos has practical implications for galaxy evolution. Galaxies are anchored within dark matter halos, their formation and stability governed by the gravitational cradle these halos provide. Within Bootos, the scarcity of dark matter means galaxies form more slowly, remain smaller, and struggle to retain the gas necessary for sustained star formation. This contributes to the observed characteristics of void galaxies, their low metallicity, weak star-forming activity, and generally primitive structures. Furthermore, the lack of dark matter impacts the flow of intergalactic gas. Without sufficient gravitational pull, streams of cosmic gas avoid the void, preferring to travel along filaments toward dense clusters. This starvation of raw material exacerbates the isolation of void galaxies, condemning them to a slow, quiet evolution. Starved of the resources needed for cosmic growth, they remain stunted, relics adrift in a sea of absence, their fates dictated by the missing gravity around them. The implications stretch beyond Bootos. By studying these extreme environments, cosmologists gain critical insights into how the universe's larger structures evolve and how dark matter shapes or fails to shape the fabric of space. Observations of void dynamics refine our measurements of cosmological parameters, help calibrate models of galaxy formation, and test the behavior of dark energy in the most pristine environments. In the coming decades, new instruments promise to deepen this exploration. Surveys like the Vera C, Rubin Observatory's Legacy Survey of Space and Time, LSST, and space-based missions like Euclid and the Nancy Grace Roman Telescope will map the distribution of dark matter and voids with unprecedented precision. Through their lenses, the hidden architecture of the universe will come into sharper focus, and the mysteries of voids like Bootos may inch closer to resolution. Yet, even amidst these advancements, the Bootos void reminds us of the universe's vastness and its capacity to surprise. It challenges the notion that structure is ubiquitous, revealing instead that absence can dominate. that emptiness can stretch across incomprehensible distances, that even the invisible threads of reality can thin and break. As we drift onward through the heart of the Bhuta's void, we find ourselves pondering a deeper mystery. If even dark matter avoids these depths, what of the motion of galaxies themselves? What hidden currents guide their journeys around the void's expanding walls? Ahead lies the study of these cosmic flows, vast rivers of galaxies weaving through the emptiness, their paths shaped by the silent push and pull of the void's unseen hand. Within the stillness of the Bhuta void, movement continues, quiet, steady, unstoppable. Though emptiness reigns in its hollow center, the galaxies along its vast perimeter are caught in a grand, slow drift. They do not float at random, nor do they simply scatter outward under the general expansion of space. Instead, they follow coherent patterns, moving in vast, invisible streams, rivers of galaxies curving around the void's expanse, guided by forces no human eye can see, but every precise instrument can measure. These cosmic rivers are known as velocity flows, and they represent one of the most intricate and revealing features of large-scale structure in the universe. To understand them is to trace the delicate choreography of matter across hundreds of millions of light-years, to see the universe not as static islands of galaxies, but as an interconnected, dynamic system with mass, gravity, and expansion interplaying in subtle, elegant ways. At first glance, one might imagine the Bhuta's void as a simple sphere of emptiness, with galaxies pushed outward equally in every direction. But the reality, revealed through meticulous mapping and precise measurements of galaxy motion, is far more complex. The galaxies near Bhutas do not merely retreat from its center. They flow along preferred directions, following gentle arcs, twisting filaments and converging toward denser structures, like water curving around a massive stone, taking the path of least resistance, sculpted by the unseen landscape beneath. Astronomers have spent decades deciphering these motions, using the redshift of galaxies, the stretching of light caused by their recessional speed, combined with calculations to remove the baseline expansion of the universe. They have reconstructed the peculiar velocities of galaxies around the Bhuta's void. Peculiar velocity refers to the galaxy's individual motion relative to the uniform Hubble flow, and it is this deviation that reveals the hidden gravitational currents in space. What they found was remarkable. Galaxies along the edges of the Bhuta's void stream outward with higher velocities than those in denser regions, confirming the local acceleration caused by the void's gravitational underdensity. But more intriguingly, their motions are not purely radial. They curve and bend, funneling along large-scale filaments that lead toward massive superclusters beyond the void's walls. These flows form part of a vast network of cosmic motion known as the dipole repeller and Shapley attractor system. On one side of our observable universe, massive superclusters like Shapley exert a gravitational pull, drawing galaxies toward them. On the other, vast voids like Bhuta's exert a repulsive effect, not by an active force but through the relative absence of matter and gravity. The combination of these pushes and pulls creates bulk flows, sweeping galaxies along giant arcs, shaping their trajectories over hundreds of millions of years. Bhutas, in particular, contributes to the local flow of galaxies in our own cosmic neighborhood. The local sheet, the structure containing our Milky Way and neighboring galaxies, experiences a gentle drift away from the Bhuta's void, contributing to its peculiar velocity relative to the cosmic microwave background. We are, in a sense, participants in this grand movement, our galaxy not static in space but riding the slow, majestic current sculpted by nearby voids and distant attractors. The cosmic rivers around Bhutas are not uniform in speed or direction. They reveal gradients, with galaxies closer to the void's edge moving faster than those embedded within adjacent walls, and with flow lines bending toward filaments connecting to other superclusters. The patterns resemble eddies and streams in a massive river system, flowing not with water but with galaxies and the invisible scaffolding of dark matter. These flows also have measurable consequences on the large-scale distribution of galaxies. Over cosmic time, the void's expansion and associated velocity flows contribute to the anisotropic clustering of matter, meaning the spatial arrangement of galaxies shows directional dependence, reflecting the dominant paths carved by gravitational dynamics. It is this phenomenon that helps explain why galaxies are not scattered randomly in the universe, but align along arcs, sheets, and elongated structures. To visualize these currents is to embrace the full majesty of the cosmic web. Imagine a glassy, three-dimensional river, millions of light years across, populated not with water droplets but with glowing islands of stars. These galaxies glide slowly, shifting their positions over hundreds of millions of years, responding to the faint tug of gravity and the gentle push of cosmic expansion. Their motion is not chaotic but follows vast loops, with some paths spiraling inward toward dense clusters, others bending outward, evacuating the growing void. Simulations of the Bootes region confirm these pathways. Advanced cosmological models run on supercomputers replicate the emergence of void-driven flows. They show how initial density fluctuations in the early universe evolved into the complex network we observe today, where voids like Bootes expand and drive outward flows, while nodes of extreme density pull matter inward, creating a dynamic balance of expansion and contraction across cosmic scales. But even in these sophisticated simulations, the scale and coherence of Bootes flows remains striking. The Bootes void is large enough to influence galactic motion across nearly 500 million light years. Its underdensity significant enough to accelerate matter outwards and contribute to bulk flows in its surrounding regions. There are deeper implications. These flows act as gravitational fingerprints, revealing the distribution of both visible and dark matter. By studying the peculiar velocities of galaxies, astronomers can map the unseen mass that shapes the cosmos. The Boote void, through its influence on these flows, becomes not just an empty space but a tool, a gravitational lens into the distribution of the most elusive components of the universe. Moreover, these patterns help refine our understanding of cosmic acceleration. The combined study of void expansion rates and galaxy flow velocities provides independent tests of dark energy's behavior, constraining its properties beyond mere measurements of distance and redshift. Every drifting galaxy becomes a messenger, its motion encoding secrets about the universe's most mysterious force. As we continue to map these cosmic rivers with greater precision, aided by next-generation surveys and more sensitive instruments, we stand on the threshold of new discoveries. Perhaps these flows will unveil subtle anomalies in the behavior of dark matter, or uncover regional variations in the influence of dark energy. Perhaps they will expose inconsistencies in our standard model, hinting at deeper layers of reality. For now, they whisper of the cosmos' dynamic heart, where nothing is ever still, where even the deepest void sets galaxies adrift in slow, majestic motion. As we trace these grand currents, our journey through the Boote void draws toward reflection, not only on its present influence, but on its prophetic significance. For the flows we observe today may be a prelude to the future state of the universe, a vast hollow expanse where matter retreats to the periphery, and islands of light grow fewer and farther between. In the next step, we will turn our gaze forward, pondering the fate of cosmic structure in the face of unstoppable expansion. What does the Bootes void reveal about the ultimate destiny of galaxies, stars and civilizations adrift in an ever-accelerating universe? The Bootes void is not just a haunting scar of emptiness in the fabric of the cosmos. It is a mirror, reflecting not only the peculiarities of the present, but foreshadowing the trajectory of the universe itself. As we drift along the sweeping galactic flows and skim the immense hollow spaces where galaxies refuse to gather, we cannot help but see a chilling future unfurling before us, a vision of what the cosmos is becoming. In the present age, the universe still pulses with activity. Galaxies collide, stars are born, planets condense, and life, at least in our tiny corner, contemplates its own existence. Yet surrounding this bustling activity, the voids grow. The Bootes void expands steadily, its borders pushing outward, devouring the tenuous strands of the cosmic web. And this quiet, slow expansion of emptiness offers a harrowing glimpse of the universe's far-off destiny, a future where voids reign supreme and the islands of light are drowned in an ocean of dark silence. To understand this cosmic destiny, we must revisit the most profound revelation of modern cosmology, the discovery that the universe's expansion is accelerating. Dark energy, a force that remains enigmatic despite years of study, is driving space itself apart. Galaxies are not merely drifting with momentum from the Big Bang, they are accelerating away from each other, pulled apart by the stretching of the very fabric of reality. In this accelerated future, the large-scale structure of the universe will unravel. Filaments will thin, clusters will become isolated, and voids like Bootes will continue to swell, consuming the regions around them. Simulations predict that the existing voids will merge, bleeding together to form megavoids, so vast and empty that entire superclusters will appear as tiny specks floating at their perimeters. Billions of years from now, the fate of galaxies will be determined by their location. Those fortunate enough to be gravitationally bound within clusters will remain in small, isolated pockets of activity, but galaxies on the outskirts, especially those in less dense environments, will be carried away by the accelerating expansion, disappearing beyond the cosmic event horizon forever unreachable from one another. The Bhuta's void, colossal as it is today, offers a preview of this isolation. Within its borders, the few surviving galaxies already exist in exile, separated by distances that make interactions nearly impossible. Over cosmic time, the rest of the universe will come to resemble Bhutas, a hollow realm where the night sky is barren, where galaxies vanish one by one, and where observers, should they exist, will be trapped in tiny oases of matter, surrounded by infinite nothingness. For civilizations peering into the future, this fate carries profound consequences. Imagine standing on a distant world, billions of years hence. The night sky would be nearly empty. The familiar glow of neighboring galaxies, Andromeda, Triangulum, the many satellites that today grace our telescopes, would be gone. The only visible objects would be the local cluster of galaxies, gravitationally bound and immune to the stretching of space. Beyond that, the universe would be a black, starless void, the cosmic microwave background stretched into oblivion. The evidence of the Big Bang faded into darkness. Cosmologists have coined the phrase cosmic loneliness to describe this eventuality, a future epoch where the universe's grand narrative becomes hidden, where even the most advanced civilization would struggle to decipher the origins of their existence. Without access to the distant galaxies, without the CMB as a backdrop, the clues that point to the Big Bang and cosmic evolution would be erased by expansion itself. Bhutas teaches us that this isolation is not merely theoretical. It is already taking form. The dynamics we observe around its periphery, the quiet abandonment within its core, are miniature rehearsals of a universal play whose final act is scripted by dark energy. This realization has driven some of the deepest philosophical reflections in modern science. Will the universe in its far future become a cold, dead expanse, dominated by voids like Bhutas, dotted only by the remnants of ancient galaxies, slowly decaying into black dwarfs and evaporating black holes? Or is there more to discover? New physics that could alter this destiny? Unknown forces that could slow or reverse the expansion? Some speculative theories offer slivers of hope, or at least mystery. Models involving quintessence, a dynamic form of dark energy, propose that the acceleration could change over time, potentially halting or reversing. Other radical ideas suggest a cyclic universe where after a period of expansion, contraction resumes, leading to a new Big Bang. But the prevailing consensus, supported by current observations, leans toward a cold, dark and empty fate. A heat death of the cosmos where entropy reaches its maximum and motion itself becomes meaningless. Even within this bleak forecast, pockets of complexity persist. Galaxy clusters fortified by mutual gravity will survive the longest. Within them, stars will continue to form from recycled gas for trillions of years, though at a dwindling rate. Black holes will continue to feed, to merge, to spin, until their slow evaporation spans timeframes beyond human comprehension. If intelligent life persists or re-emerges in these distant epochs, its relationship with the cosmos will be profoundly different from ours. The grand vistas of galaxies, nebulae, and the cosmic web will have faded, replaced by an intimate, claustrophobic universe of local phenomena. Bhutas, then, is more than a void. It is a time capsule, a window into the inevitable future, a lesson in cosmic impermanence. It warns us of the transience of structure, the fleeting nature of cosmic complexity amidst the relentless tide of expansion. And yet, standing here, imagining ourselves adrift in this emptiness, there is a strange sense of peace. The universe moves according to laws far beyond human intervention, evolving through cycles of chaos and order, clustering and dispersion. In contemplating Bhutas, we confront the brevity of our moment in cosmic history, but also the wonder of existence within this fleeting window of galactic brilliance. As we prepare to descend deeper, we ask one final question. Is the void truly empty? Could there be hidden phenomena lurking within its depths, ultra-faint galaxies, unseen particles, or exotic structures that escape our current detection before the universe fades, before cosmic expansion completes its final quiet triumph? We turn our gaze back into the heart of the Bootes void to search for the faintest remnants of structure that might persist, cloaked in the quietest shadows. We drift deeper now into the heart of the Bootes void, where emptiness seems absolute, where the blackness feels thicker, heavier, pressing in from all directions. From a distance, this void appears nearly featureless, a cavernous realm stripped of galaxies, stripped of light, stripped of motion. But emptiness is rarely absolute in the cosmos, and here within this colossal hollow, subtle signals whisper of hidden structures, faint and elusive, scattered like cosmic phantoms in the shadows. Astronomers, armed with ever more sensitive instruments, have begun to peel back the silence of the void. What they have uncovered is surprising. Though the Bootes void is remarkably underpopulated by the standards of cosmic structure, it is not entirely barren. Its depths conceal tiny, dim galaxies, so faint that early surveys missed them entirely. These are the ultra-diffuse galaxies, UDGs, ghost-like systems with few stars, sparse structure, and a strange resistance to the gravitational tides that shape their brighter cousins. UDGs are difficult to detect. They barely glow, their surface brightness hovering at the edge of detectability, often lost amidst the noise of distant background radiation. Yet, within voids like Bootes, their discovery has opened a new chapter in our understanding of galactic survival. These galaxies are relics, ancient, fragile structures that managed to form stars before the void expanded around them, then survived in isolation, cut off from the bustling ecosystems of denser environments. Some of these phantom galaxies exhibit odd properties. Their rotational speeds imply the presence of disproportionately large amounts of dark matter relative to their meager stellar populations. It is as though these galaxies are little more than dark matter halos with a thin scattering of stars clinging to their gravitational grip. Others, curiously, seem to lack sufficient dark matter altogether, their dynamics hinting at unknown mechanisms that allow them to remain gravitationally bound despite their fragility. In the Bootes void, these shadowy galaxies raise new questions. How do such fragile systems form in an environment starved of matter? Why do they persist, untouched by the galactic cannibalism so common in denser regions? Some scientists theorize that void galaxies may retain more primordial characteristics. Their stars are older, their gas less enriched, their structures less disturbed, making them living fossils of the early universe, untouched by the mergers and collisions that shaped galaxies elsewhere. Beyond these faint stellar outposts, astronomers have also detected diffuse flows of gas within voids, wispy threads of hydrogen, invisible to optical telescopes, but revealed by radio surveys. These gaseous structures suggest that the void is not entirely empty, but threaded with cold, pristine matter, remnants of the early universe that never condensed into galaxies. Though tenuous, these hydrogen streams are significant. They may act as the lifeblood of void galaxies, offering rare material for slow, sustained star formation over billions of years. Instruments like the Green Bank telescope and the Mercat array have begun mapping these faint hydrogen emissions, revealing a hidden skeleton of structure invisible to the human eye. Even in Bootes, these faint signals emerge, hinting at ultra-thin filaments crisscrossing the emptiness, connecting isolated galaxies like a gossamer web stretched almost to the point of breaking. Some cosmologists propose that within these filaments, undetectable by conventional light, may lie exotic forms of matter, perhaps variations of dark matter, or even speculative entities such as axion fields or dark sector interactions. While evidence remains elusive, the Bootes void is quickly becoming a prime target for experiments, seeking to probe the most elusive components of the universe, precisely because its emptiness offers a quieter, cleaner backdrop against which to detect rare or subtle phenomena. Moreover, the extreme underdensity of Bootes offers a unique environment to study how cosmic structure behaves when freed from the dominant gravitational interactions of massive clusters. Without the overwhelming presence of nearby giants, void galaxies evolve slowly, allowing astronomers to study internal dynamics. From the gentle rotation of gas clouds to the muted flickering of ancient star clusters, in near isolation, This provides an unparalleled opportunity to refine models of galaxy evolution without the noise of frequent galactic mergers or violent gravitational encounters. As observational techniques improve, even fainter candidates for hidden structures emerge. Some astronomers suggest the possibility of isolated rogue black holes wandering the void, remnants of ancient galaxies that were completely stripped away by gravitational interactions, leaving behind only their invisible compact cores. These black holes, moving silently through the darkness, might reveal themselves only through subtle gravitational lensing effects or rare flares when encountering sparse intergalactic gas. There are also the faintest possible signatures, hypothetical dark galaxies, systems composed almost entirely of dark matter, with no stars to mark their presence. While purely speculative for now, such entities could exist within the Booty void, their gravitational fingerprints only barely detectable through their influence on the motion of nearby visible matter or through their interaction with intergalactic gas streams. Some of the most sensitive radio and gravitational surveys in the coming decades, including the Square Kilometre Array, SKA, hope to probe these possibilities, targeting void regions like Bootis precisely because of their uncluttered nature. In a universe crowded with competing gravitational sources, voids may act as pristine laboratories, places where the subtlest structures and interactions can be observed with minimal interference. Yet for all these hidden possibilities, the overriding sensation within the Bootis void remains one of absence. Even with advanced detection techniques, the population of galaxies remains drastically lower than statistical averages. The few ghostly structures we find serve not to contradict the void's identity but to deepen its mystery, raising further questions about how much quieter, simpler, or stranger cosmic evolution becomes in the absence of crowding. In philosophical terms, the Bootis void invites reflection on balance, on the contrast between presence and absence, structure and emptiness, abundance and scarcity. In the bustling hubs of superclusters, galaxies are born rapidly, evolve violently, and burn out in dramatic displays. In voids, galaxies live quietly, evolve slowly, and persist far longer, like distant embers glowing faintly in an ever-chilling hearth. As we slowly ascend from the deepest depths of the Bootis void, leaving behind its fragile orphans and hidden filaments, we carry with us a deepened understanding that even the loneliest corners of the cosmos are not entirely barren. They harbour remnants, whispers of the past, subtle traces of the forces that once shaped them. Ahead lies the final reflection, an examination of what the Bootis void ultimately teaches us, not only about the nature of the universe, but about our fleeting presence within it, and the haunting beauty that lingers in even the most silent expanses. As we leave the vast and hollow corridors of the Bootis void, we carry more than observations, more than measurements of expansion rates or peculiar velocities. We carry a profound lesson. In the universe's silence there is wisdom. The Bootis void, in all its emptiness, speaks to us in a language of absence, revealing truths not only about the cosmos but about our fleeting existence within it. For in the spaces where galaxies fail to gather, in the cold stretches where light grows thin, we uncover reflections of the universe's history, its future, and perhaps something quietly human. It is easy to look into the void and see only nothingness, a barren chasm devoid of stars, a silent graveyard of galaxies, a realm where cosmic architecture collapses into minimalism. Yet, as our journey has shown, even within this emptiness, subtle structures persist. Fragile galaxies, hidden filaments, phantom flows. The void is not simply the absence of matter. It is an active force shaping the universe by its very emptiness, driving the flows of galaxies, sculpting walls of resistance, stretching light itself thin. In the Bootis void, we see the interplay between attraction and repulsion, between gravity's binding embrace and dark energy's quiet push. The void reminds us that the universe is governed not only by the power to build, but by the inevitable force to disperse. Creation and dissolution are interwoven. Just as galaxies form from collapsing clouds, they also vanish into cosmic isolation. Just as clusters gather matter, voids carve it away, sending it adrift into the expanding night. For scientists, Bootis offers a critical vantage point. It challenges our cosmological models, stretching the limits of simulations, urging a deeper understanding of dark matter, dark energy, and the initial conditions of the universe. It demonstrates that in the universe's grand design, Exceptions and extremes are as instructive as averages. By studying emptiness, we learn more about structure. By measuring isolation, we understand connection. By tracing the flow of galaxies away from voids, we reveal the hidden contours of the cosmic web. But beyond data and theory, the Bhuta's Void offers a humbling philosophical reflection. It shows us how fragile structure truly is, how fleeting the presence of galaxies and stars can be amidst the overwhelming tendency of the cosmos to expand, to empty itself, to fade. It confronts us with the impermanence of the universe's visible splendor, with the reality that cosmic grandeur is temporary, destined to unravel under the quiet, persistent pull of time. And yet, within this silence, there is beauty. There is elegance in the patterns of the void walls, and the hidden symmetry of the Bush tube, and the delicate survival of orphan galaxies floating in the dark. There is wonder in the void's influence on the ancient light of the cosmic microwave background, in the subtle flows of galaxies tracing arcs around an unseen heart. There is mystery in the absence of dark matter, in the whispers of faint hydrogen streams, in the possibility of unseen forces at play. In contemplating the void, we are reminded of our own place in the cosmos. We inhabit a small planet orbiting a modest star, nestled within a quiet corner of an ordinary galaxy, itself one among billions. The Milky Way orbits within a local group, which in turn is drawn toward clusters and filaments, all interconnected within the cosmic web that spans billions of light years. And yet, surrounding this fragile latticework is a sea of emptiness, voids stretching across intergalactic space, growing steadily, slowly severing the connections between galaxies, drawing the universe into ever-deepening isolation. Our era, then, is special. We exist in a cosmic moment when the universe is young enough that galaxies are still connected, when the sky is rich with distant light, when the echoes of the Big Bang are still visible in the CMB. A time will come when that light will fade beyond our reach, when galaxies will vanish behind cosmic horizons, when the universe will grow cold and silent, resembling the interior of booties stretched across all existence. This fleeting moment of light invites a quiet gratitude for the ability to look up at the night sky and see the brilliance of neighboring galaxies, to study the structures that surround us, to explore the depths of the universe and trace its history. In the distant future, such knowledge may be impossible to acquire, and yet here we are, alive in an era where the cosmos speaks openly through its light, its flows, its structure. Bhuta's teaches patience too. The galaxies within it evolve slowly, undisturbed by violent mergers, left to age in peace. Stars flicker within ancient galaxies, gas drifts lazily along cold streams. Structures change on timescales far longer than human history. In contrast to the haste of human life, the void offers a vast, calming perspective, a reminder that change can be slow, that silence can be profound, and that existence in all its scales unfolds patiently over eons. As we gently withdraw from the Bhuta's void, from its growing emptiness and its whispered secrets, we are left with more than scientific curiosity. We are left with wonder, a wonder that exists not only in what is visible, but in what is missing, a reverence for the forces that gather matter together, and a respect for the forces that inevitably pull it apart. The universe breathes in cycles of clustering and isolation, creation and entropy, and in the Bhuta's void we witness the great inhale of silence. Returning now to our small world, our blue dot orbiting a quiet star, we carry the lessons of the great void, to cherish the fleeting connections we have, to marvel at the structures still visible in our sky, to remain curious in the face of the unknown, and to embrace the quiet, beautiful truth that even in the deepest silence there is something to learn. The void does not shout, it whispers, and we, for a brief luminous moment in cosmic time, have been here to listen. Now allow the distant echoes of the Bhuta's void to fade, like the final glimmer of a star sinking beneath a cosmic horizon. Let the vastness recede, and bring your awareness gently back to the rhythm of your own breath, to the quiet pulse of life here and now. From galaxies to voids, from swirling clusters to empty space, the universe unfolds in grand, sweeping scales, but within you, a quiet cosmos remains, calm and steady. Rest now in the knowledge that you have journeyed across billions of light years, touched the edges of existence, and returned, wrapped in the soft serenity of cosmic understanding. Let your body sink into comfort, your thoughts dissolve into stillness, and your breath carry you into gentle sleep. All is quiet, All is vast, all is well. Good night, Voyager of the stars.